Alright. Good morning. Any questions or comments? Okay. So I'll start to talk about the new chapter. I'll use bare face. So I think the basic idea is quantum mechanics has a phase degree of freedom, and if you change the parameters of the Hamiltonian, okay, if we change the parameters of system, this phase endows non-trivial structure. Okay, so we are going to see that, and this non-trivial phase is called bare phase. Basically, if you start, okay, let me introduce the model and then the setting, and then we can talk about that. Let's consider a set of parameters. I'll use R for this, but this is not the vector in 3D. It's going to be R1, R2, RD. So this is like a d-dimensional parameter space, and we imagine Hamiltonian depends on these parameters, and there is like some h which depends on r. So it is like a vector, but I will not write vector and t every time, not to clutter the equations. So this is acting on exact eigenstates. Again, this r and t. In a little bit I'll drop both arrow and t is going to be equal to e nth eigenstate, and there is like an r dependence there too. It's going to be equal to n r and t. Good. And what we are assuming is this spectrum En of R is discrete, or sometimes people say there's a gap. It's like a gapped spectrum and non-degenerate. So the gap is mandatory. If you don't have gap, you cannot talk about bare phase. But non-degeneracy is optional. You can also do exactly the same thing for degenerate manifold. In that case, it's going to be non-abelian bare phase. It's going to be like a matrix phase. And what we are assuming is we start psi at t is equal to 0 is one of the eigenstates. Let me write it like this. It is going to be n of r0, like I'm dropping the vector now. It's too much writing. And starting from this, like we evolve r of t and ask how psi evolves. Okay. So the time evolution in quantum mechanics has like two contributions. One is what we call dynamical phase. So it is like usual e to the minus I over h bar epsilon n times t. But in this case, you can see epsilon, each eigenvalue is r dependent, and r depends on time. So we have to generalize this, and generalization is just integral of this thing. So this dynamical phase takes the form minus I over h bar, some integral from 0 to t, dt prime e n r of t prime. But in addition to this, because of like a complex nature of eigenstates, we also allow like a so-called geometrical phase, and this will turn out to be Berry phase.
Is this a topological phase?
It will be. At the moment, we don't know nothing, right? We are trying to introduce, so we start from this, and we slowly evolve R, and we are asking what happens to a state if I start from an exact eigenstate. And at the moment, this looks like a trivial phase, but it will turn out to be not trivial. It will turn out to be quite profound in a little bit. So I'll call this geometrical, like Berry phase, and I'll show it like with e to the I gamma, and it can depend on eigenstate, and it can depend on time, but that's it. And this thing has been dropped in like for 80 years until Berry came up. People thought this was like a trivial overall phase, and they didn't consider the dynamics of this phase. So then overall psi of t is going to be this e to the I gamma n of t, that's the trivial phase, e to the minus I over h bar from 0 to t dt prime epsilon n r of t prime, and also this n r of t. So what we are saying is, okay, let me also pull that down. Maybe this is a little bit up. So what we are saying is that we are starting from an eigenstate of Hamiltonian at R of 0, and as you evolve, and we are saying that the evolution has to be adiabatic. What this means is like it has to be very, very slow. We can also make this statement very quantitative, but it is not very important. We slowly change R, and what we are saying is this state, which is an exact eigenstate, is going to evolve to exact eigenstate at R of t up to these two phases. One is dynamical phase, the other one is geometrical phase. And now we want to find this object in terms of the dynamics of the system. So for this, we require Schrödinger equation, right? We have to have wave equation. That's not optional. So I h bar del t psi of t should be h r of t psi of t. So we are at any moment we are evolving with Schrödinger equation, but Hamiltonian given by h r of t. Quite non-trivial things are set up here, but they are simple to understand. So I want to plug this in here, and I want to call this entire phase. So let me call this entire thing, maybe excluding I. So this entire thing. Let me call this theta. Not to have to write entire thing over and over again. So if I act on derivative can act on this and act on that, and there will be and this one is going to have two components. In total, derivative acting on this or this is going to give three terms here, and I'll open this up. So first, after derivative acted, this e to the I theta will move to the left, and we have I h bar. So this derivative acting on gamma is going to give us I del gamma n del t. Now derivative acting on here is going to be I h bar minus I over h bar, and derivative of integral is integrand. So this is going to be e n r at t. And lastly, derivative acting on this guy. So this is going to be I h bar del t and r of t.
There should also be epsilon at t equals 0.
Like I think fundamental theorem of calculus says like if you have d dx from 0 to x, the x prime f of x prime, this is f of x.
Fx minus f of 0.
In this form, there is no f of 0, right? There is, because you are just taking the derivative.
It's the second one. This is the first one, fundamental theorem. The second one, if it was inside.
There's also f of 0 in there.
No. If the derivative was inside, then it would be f.
Oh, yes. If the derivative, yes. Now that's what you mean. I got it. Yes. So this is the left-hand side, and right-hand side is going to be e to the I theta, right? This overall phase is going to just move around the Hamiltonian, it doesn't mind. And this thing acting on n of r is going to give e n of r of t times n of r of t. Okay, so this is the equation. First, this e to the I theta did its job, and thank you, and we just get rid of it. And you can see I minus I is 1, h bar 1, epsilon, this epsilon is going to cancel this epsilon, so this is also thank you. What remains is like these two terms. And let me first write and then manipulate. So this is going to be minus h bar del gamma n del t acting on n of r. Now I leave the time explicit because I took care of time. Plus I h bar del over del t n of r. I think this h bar it can also be cancelled. Right. Now I take product with n of r both sides. Then this is going to give me. Did I miss like a overall sign? Oh yeah, no. This entire thing is equal to 0, right? So then integral will give del gamma n del t is going to be equal to I n of r del t n of r. So this is the first non-trivial result. Now we can integrate this, and we can integral of this thing is going to be, so this okay, integrate gamma n is going to be equal to I. Now let me put this t prime. This is dt prime n of r t prime del t n of r t prime, and the integral I'll take it from 0 to some t.
Is it del over del t gamma n, or it's expected value?
So this is del over del t gamma n. Oh, this is equal to, right?
How can we just take it outside?
Because this is overall a number. If you just take nr, right? Numbers just commute with nr, and nr, they are orthogonal. But this one is not a number. This one is an operator. Because yeah, that's the good point. Thank you. And here I want to do a change of variable here. So this one I want to write. Let me do it in 2 lines. So this one I want to write it like so the r del r, right? Because Hamiltonian doesn't depend, the state does not depend on t explicitly, it depends through r, so it's reasonable to do this. And here, oh, okay, this is t prime, And here I just change the variable, right? If I change the variable, this is going to be the r dot, and I can erase this one. Good. Yes, this is a vector, like a path vector. Like this is like now it was like a time integral. I converted it to a path integral, right? And there is dr. So this object is a vector dotted onto this object, which is also a vector, and the total result is scalar, which should be, because here we have scalar.
But maybe it's path independent.
Many? Can you say again?
Path independent.
Exactly. We will come to that. At the moment, we just manipulate equations, but we'll check all of these one by one. Then, so this gamma n, I want to write it as gamma n is equal to. So what we assume here is like assume r of t is evolution in a closed loop. So what this means is that you change the parameters of Hamiltonian, but eventually you come back to where you started, right? We are interested in that. We can also look at other things, but that's the interesting one. In that case, gamma n is going to be equal to integral over this loop, whatever the loop is, the r dot sum a n, which will depend on r. So this is what we call bare face, and a here is defined from here. This a n of r is equal to I n of r del r n of r. Good.
What about timing? This is, in the iteration we have like t prime, prime.
Yes.
Was it intention?
So this time index.
Yeah.
What was intentional? Can you?
T prime in nr.
Oh, this is no. This is like a typo. No,
Okay.
this is typo. Yeah. Good. Thank you.
Shouldn't the integral ranges also change? I mean, in the first form it was 0 to t.
Yes.
But now we did a change of variables.
Exactly. It was 0 to t, and we assume like evolution in a closed loop means r of 0. All of these numbers should be equal to r of t. We require that. Okay. But if we can also consider if this is not equal, but at the moment the interesting one is this, and we will work on that just a little bit. So this A is called Berry connection. It is not important why it is called, it is just what it is, but there is a reason for it. I think it's not interesting. So, just to save time, like there's like a trivial exercise, like exercise. Start from, these are normalized eigenvectors, and r is equal to 1, and act with del r on both of these, and show and r del r. Okay, I am now shortening the notation slowly. I will not del at every time. I will just use this quick notation. And r is pure imaginary. Okay, right. Just simple thing. If something is pure imaginary, its complex conjugate is going to be minus of itself, right? So that's like a standard thing to see. That means gamma n, okay, so gamma has a and a has I. If you multiply a pure imaginary number with I, it's going to be pure real. That means gamma is going to be pure real. So that gamma is real, and it should be, right? Because the way we set up the problem was here, gamma, we put it as a phase, but if it was not pure real, it would imply a decay, and that would not be nice. So that also is consistent. Now let's think about these different path deformations like you asked, and also different ways of closing the loop. So this is what I'll call gauge transformation, which we spent a lot of time. So this H R n of R is equal to E and R remains invariant. So this is invariant if you take n of R and put it with an overall phase, right? Because that's what we mean quantum mechanics is defined after a phase. In that case, this Berry connection A n of R, which is equal to I and R del R and R, is going to go to itself, right? Because this derivative can, okay, every time you see an R, replace it with this, and the derivative can act on this or act on that, and we spent quite a bit of time with that kind of calculation. Let me just write the result. So what the result is going to be A n of R minus del R zeta of R. So then you can see A n is gauge dependent. Okay. But this gamma n, which we defined in the loop, let's also look at that. Gamma n, which is equal to closed loop the R dot A n of R is going to go to, right, there are two terms. One is itself, gamma n, and the other one is minus closed loop the R dot del over del R zeta of R. Now you can see this is the integral of derivative, and it is going to be gamma of R. This is the boundary that you were asking about, so this is going to be something like it. Gamma of R of t minus or zeta of R of t minus zeta of R of 0, and which is 0, right? Because R of 0 is equal to R of t, and we better have zeta to be single valued, right? If it is not single valued, we cannot do quantum mechanics, then this is going to be 0.
How do we know that there is no residue?
Well, there will be a residue. If there is like a residue, we'll see it is going to pick that up, right? But this one doesn't have it, right? So this one, it has to have smooth, right? Gauge transformation, this zeta, otherwise, right? If it is not smooth, you don't have a gauge transformation. If you have a residue, you are putting like charges, and that's you are going to a different system. You are not making a gauge transformation. So you can see already like analogy with vector potential A and magnetic field in electrodynamics, electricity and magnetism. And there we have like this dl dot A. Using Stokes theorem, you can write it like d sigma dot B, right? Standard, everybody knows that. And it is the flux. And B is related to A through this curl. and you can see we have like similarities there, then it suggests we maybe we can also define we can define this Bn of R based on this analogy, which will be called okay, let me write this. So this electrodynamics is done in three-dimensional space, but we may have like a Hamiltonian with parameters more than 3, right? We can have any number of parameters. We can go to any dimension with this machinery. Then what we need to do is like we need to generalize this to d dimension. So this Bn. So in the generalized form, let me just write it. Gamma n is equal to. So this people generally use this kind of notation. This is the boundary of some domain S is going to be given by dr dot this a n of r, and if you use the Stokes theorem in more than 3 dimensions, there's like a way to write this, and it's called wedge product. Let me write it and explain. So this is going to be dr mu wedge dr mu, and this one I use w n mu nu of r. So this is a wedge product. That means if you are in 2D, for example, you just take 2 vectors, and their wedge product is going to give you the oriented area. Right? It's not important. It's kind of like it's kind of like a cross product. Actually, it's the cross product, but for mathematicians, they like defining new things. In my mind, there's no new value to learn this. I mean, of course, you can learn this if you are going to be specialist, but at the moment, this is just area, right? Here, we have area here, we have area here, but in more than 3 dimensions, there are like some mathematical properties required that they put it in this form. So this also has like, there is like a, and the reason you won't need this is because we won't use it in more than 3 dimensions. So in 3 dimensions, we will always use this. So this is just some like, if you want eye candy for like mathematically savvy students. But Gerwin Young is also talking about that, which is I think not relevant. There's also a summation convention. There's like mu nu, because you can do double summation because you are summing over mu and nu twice. You put like 1/2 there.
There is also summation.
Yeah, there is like repeated indices are summed over here. And what is important is this thing. Let me.
Sorry. Does a symbol stand for summation?
No, this is not summation. Omega I will introduce, but summation convention says if you repeat any index, you need the sum over the index. So because we have like so many sums, you don't want to keep writing this. Some people say this is the Einstein's biggest contribution to physics. He saved us from writing all these sigma signs and mu's all over the place. So this omega, let's write this, omega mu nu of n of r is defined by del mu a n of nu minus del mu a n of nu. And del mu here is short for, you can see I'm even more shortening, del r mu, because there are so many things to write. If you write everything, you sometimes don't see what you wrote, so I shorten it a lot. So in 3D, that's the interesting one. So this Bn is going to be del r cross an, and if you plug this in, right, an was equal to I, and r del R and R. So this del is acting on here. There is one more del acting, right? So if you act them, what you are going to find is like something like that. I del R and R cross. So this is like a column vector cross product. This is del R and of R. So this is in 3D. And this B or omega, okay, double line B n or omega mu n is called Berry curvature. So we have Berry phase, Berry connection, and lastly Berry curvature. 3 new terminologies with all names of Berry, but people don't mind that. Okay, there is one last derivation, and then after that I want to take a break. There is like an alternative form to write the Berry phase, and it is a little bit tricky, at least in Gervin-Young, to make sure we go through that. I want to do it here. So, alternative form of Berry curvature. So let me start from this. H of R, n of R is equal to epsilon n of R, n of R, and act with del mu, which is short for del mu. Now we can act on here or there, and there will be 4 terms in each side. And let me spell that out. So this is del mu h of. Let me also not write r, because we know h is r dependent, right? We know that. Like, there's no point of writing it over and over again. Everything depends on r anyways. So this one, n plus h del mu n is equal to del mu epsilon n plus epsilon n del mu n. I just didn't do anything, I just acted with the derivative. Now I want to take product with n prime, and I want to assume n prime is not equal to n, right? I only take the product with different indices. In that case, it's going to be n prime del mu h n plus, actually let me not write that. So this thing n prime is equal to, so this is just a number. And when you take, right, number just go through n, and this is going to be 0, right? It's commute, and n prime are different, so it's going to be 0, plus epsilon of n prime del mu n. Now this piece I want to act Hamiltonian, right? Hamiltonian is Hermitian, it can act on this side or that side, it doesn't mind. So this is going to be E n prime, but it is not 0, there is still del mu n, and I'm going to combine this one with this one. Right, it's going to be E n minus, I wrote it E n prime. These are dependent, but I'm not writing, times n prime del mu n is equal to n prime del mu h n. Now I want to take the complex conjugate of this, so this is I. I want to write an identical equation by taking the complex conjugate, and redefining the label. So complex conjugate of this is real, so it's not going to change. If you take the complex conjugate, this n is going to move on this side. This one is going to be n prime. So this one is going to be, so this is going to be n prime. And here this, okay, let me do it in 2 steps. So this is going to be del mu n, okay, let me write it bigger, del mu n prime is equal to, so this is n del mu h n prime. So now I've taken the complex conjugate, this one and this one. Now I want to define, wherever I see mu, I want to write mu, because I'm going to do this for 2 different indices. This is n prime, this is n del mu, okay, that's, and now I want to take the product I times I and get the result. So this is going to be En minus En prime squared this thing times this thing is equal to, and now I want to write this as like del mu h. So this is like a matrix element of this. If you want, this is like a velocity operator, right? If you take the derivative of Hamiltonian, it's kind of like a velocity operator. So this is going to be n prime n, and this is del mu h n prime. And I want to take this to here. Okay, let me write it in 2 lines not to lose track. So what I want to do is I want to take this to other side, because n and n prime are not equal anyways. And this is the denominator. So let me just center that. And I want to sum over all n prime, right? I just do this n prime. So if I do that, so this is going to be identity, so I can just get rid of the sum here and erase this, but this one is going to survive a summation sign. So there's the meaning is like n prime summation over n prime, but it should not be equal to n. Good. Okay, I think I messed up this a little bit. Del mu n.
This looks like correlation.
Exactly. It looks like perturbative correction, right? The second order perturbation, but you can see we didn't do any approximation there. This is actually exact, but it has the same structure of second order perturbation theory. So which hopefully, if we'll have time and we'll see things like Kubo formula, something like exactly like this will show up there, and we'll connect that result to this topological result. So then, okay, I can write 2 of these, right? This omega mu nu. So omega mu nu is del mu a and mu, and inside this we have, I think, okay, a. Inside a we have this, and omega we have one more derivative. If you plug this all in, what you find is like this thing minus its complex conjugate is del mu nu. Let me just write that. Omega mu nu n is equal to this thing. And let's extend this minus this complex conjugate. And here, okay, at the moment there is no factor of I. You can see there is a factor of I here which was missing, and that factor I'll just write it hand. Okay, this is exactly, okay, first this is non-perturbative, and it should be identical with what we had here, right? This this form and this form. But sometimes in some problems this is more useful. Like for example, Bloch electrons in a magnetic field, right? There's like this Bloch vector, and hopefully we'll see that in this week or next week how this formula will apply there. So maybe I can take a 5-10 minute break and continue in the second hour. Any questions?